Thanks, Matt. Let's see. There we go. So let me get my screen shared. All right. As Matt said, my name is Wes Donald. I'm with the Auburn University Stormwater Research Facility here in Auburn, Alabama. And today I want to talk about kind of a broad topic. And it's something that just kind of has popped into my mind and piqued my interest here probably the past few months. So this is kind of my own opinion, I guess you could say. It's just something that I thought about maybe a good approach to think about. And so, a lot of this is going to be kind of my thought process on controlling stormwater, managing stormwater, especially how it applies to the construction stormwater and managing and minimizing pollution coming from it. So, as Matt said, our topic today is controlling construction stormwater should go beyond stormwater management. And we'll talk about a few key points to that discussion. To introduce myself, again, my name is Wes Donald. I'm a research fellow here at the Stormwater Research Facility. I've been in this role of probably 12 years, but been with the facility itself probably about 17 years. I started there performing work for my graduate program. So I've seen the facility change. I've seen our approaches changes, and I'll take some time to kind of discuss some of that today. One of the things that Barry Fagan likes to quote is, leaders never start with what needs to be done. Leaders start with why we need to do things. And the quote goes on from there, but today my discussion is really going to focus on the why of things. Why are we doing the approaches that we are, and maybe why should we change our process of thinking about how to approach stormwater management as it relates to construction stormwater. So, a topic that we've seen a lot, obviously, construction stormwater increases erosion rates by 100 to 200 or 1,000 to 200,000 times greater than natural areas. And this picture just paints a broad stroke of what that means and why that is. Again, today I'm talking about control, and when I look at this picture, how much control is there within the site to minimize pollution? And that's really the goal of stormwater management, is to minimize the pollution that we're creating from our projects. Construction activities are the largest human-induced non-point source of sediment. So non-point source pollution comes from many diffuse sources rather than a single identifiable location. And that's really the issue that we have with non-point source pollution. When the Clean Water Act was proposed and developed over 50 years ago, the initial idea was obviously to clean up our waters, but it was to force industry to minimize the pollutants that they're discharging from their manufacturing plants and water treatment plants and things of that nature. And we're talking discrete points of entry. We learned very quickly that type of industry that controls where the water is coming from, what's going into the water, can also figure out how to get the pollutant out of the water before it sends it off site. And very quickly, that industry did a great job of meeting the needs of the Clean Water Act. Unfortunately, we are still struggling with non-point source pollution because of that issue. We don't have full control over where that water is going all the time and where it's coming from all the time and how it's impacting and how we can treat it. So 40 years later, 50 years later, we're still the leading source of impairment within the U.S. Our facility was developed with the ideas we need better best management practices. We were having, especially, early mid-2000s, we were having a lot of issues in the state related to construction stormwater, and AU.ie was one of those issues. And they'll be the first ones to raise their hand and say that we weren't doing it well enough. And they came to us, the civil engineering department here at Auburn, and said, can you help us come up with solutions for this? And that's really when our facility was developed with a partnership with AU.dot. We created the Auburn University Erosion and Sediment Control Testing Facility. So that's who we were. We're this, small, quaint facility out at the NCAT test track. Our original name, Erosion and Sediment Control Test Facility, obviously it doesn't really roll off the tongue very well, but it defined who we were. Again, I started there when that building that you see down at the bottom wasn't even that size. It was about 2/3 of that size. And this area was fully wooded. And we went in, cleared the trees, built ponds, built our drainage channels, built our test channels. And I set out focusing on testing ditch checks, the largest sediment control BMP probably used in the state, at least on highway construction projects. And for those of you that are hopefully still paying attention, I did say sediment control, because at the time, that's what we thought that they were, and that was our approach. And, as we tested, as we learned, and we were kind of in the infancy of learning this stuff as well, our approach changed. We realized that things like check dams and ditch checks are technically erosion controls. So changing perspective is something that we had to do, and hopefully it's something that we will continue to do. So in 2020, we took some funds that we had available, and we increased our footprint. We increased our capability to test out of the facility. We went from just over 2 acres to just under 10 acres. We built larger ponds, and now we have a much larger infrastructure that allows us to go out and evaluate construction BMPs. So who are we now? We are the Auburn University Stormwater Research Facility. After we went through the expansion, Dr. Mike Perez said, I don't love the name, and none of us really love the name, Erosion and Sediment Control Test Facility, because it did define who we were, who we thought we were, but it really didn't define, or it didn't really roll off the tongue. It wasn't something that we could easily create an acronym for or anything like that. So Mike came up with a bunch of different names, and he said, I want us to be the Stormwater Research Facility. And I did not love the name because it did not define the erosion control part and the sediment control part, the things that we really focused on testing. And it really took me a while to come around to it. And honestly, as I've been thinking about this discussion, there couldn't have been a better name for the facility, because the focus, and what I'll discuss today, is the focus really should be on the stormwater part. If we can focus on the stormwater, then we can better manage the erosion and sediment from our projects. So stormwater runoff, it's defined as precipitation that impacts the ground, but does not soak into the ground and instead flows over land surfaces. And we think about how it's managed in nature. It's balanced by topography and ecosystem. There is excess runoff. It runs to the nearby water bodies, but it's in balance with the environment around it. And it's how it's basically evolved over the years and decades and hundreds of years of being in balance with the water that it typically sees throughout the year. Urban areas, we strive for balance, but we definitely take a planned approach. We figure out the best ways to manage it. We figure out ways to treat it. We do have more control over it, even though we call it management, and that's not a bad thing. We typically, except for the most extreme events, are able to control the stormwater. Construction settings, I think stormwater management is intended by the BMPs that we use, but I don't know how far we go into actually asserting ourselves into managing and controlling the stormwater. Stormwater, and I kind of paused here when I was thinking about this, because when I think about stormwater, it's a problem. And I didn't really want to say stormwater is a problem, stormwater is an issue. It's an abundant resource we have in the U.S. Mobile, Alabama is the wettest city in the U.S. Pollutants are carried, overland flow, and it becomes a perpetual issue, especially in our subtropical areas. So when it comes to construction, we know construction efforts exacerbate our stormwater pollution. With sediment being that main pollutant, we try to control it with erosion and sediment. We try to manage stormwater on our project, but how far or how well are we actually managing stormwater, and how well are we controlling erosion and sediment? State and federal manuals typically say we control erosion and sediment, but we manage stormwater. You'll find some that'll say things like temporary stormwater control measures, but for the most part, our manuals talk about managing stormwater, but controlling erosion and sediment. And I have to ask the question, do you feel in control of erosion and sediment? Um, I feel like the answer probably is no. We do things that we try to minimize its impact, but I think about control. I think about I got to be in control of my vehicle. When I'm driving down the road, if I'm not in control, I'm going to get hurt, or I'm going to hurt somebody else. I'm not managing the vehicle. I may manage my destination by picking the path to go in, but I have to be in control of that vehicle in order to complete the task that I have at hand. And so when I think about control of a vehicle, controlling, a television, we have a clicker in our hand and we're adjusting volume and adjusting channels. We are in control of what's happening and what we're seeing. But on a construction site, do we feel like we're in control? And do we manage or do we control construction stormwater? Or is it both? If we define control, is to determine the behavior of something. We are affecting the behavior and the outcome. From an engineering standpoint, we are coming up with interventions to stop or reduce specific impacts, whatever that goal may be. Whereas management is a broad strategy to minimize risk. And from a construction standpoint, the risk associated with stormwater is typically going to be that pollutant discharge that we're trying to minimize. So again, another question, does our attitude when it comes to controlling or managing, does that reflect our intent? If we're trying to control erosion and sediment, that's our intent, but are we putting forth the effort and the processes that we need to think about throughout the design in order to get that control that we're looking for? So managing stormwater is going to require an understanding of its characteristics. Where is it coming from? Is it coming from the land itself that we're working on? Is it coming from somewhere else onto the land that we're working on? Where is it going? What are the impacts and the risks associated if it's not properly managed? These are things that you think about as you're considering how to design and manage it and oversee a construction project. But again, management is planning. So we plan for the storm events that we predict are going to be for the 1, 2, 3 year time period we're under construction, as well as the drainage areas that we're managing and that's producing the runoff. And from that, we're determining volume, we're determining flow paths, we're determining peak flow rates. And these are all things that we need to do, but determining does not mean controlling. And again, controlling is something that we really need to consider. We think about our handbook, the Alabama Blue Book. The title of it is Erosion Control, Sediment Control, and Stormwater Management on Construction Sites and in Urban Areas. And I think a lot of times we forget about the stormwater management and the urban area side. We simply see this as a way to advise us on how to control sediment and erosion on construction sites. And it goes beyond that, and as well it should. Looking at the things that we have available, the tools we have from this manual, site prep, surface stabilization, runoff conveyance, right there we have a stormwater control, sediment control, obviously. Stormwater management is actually talking about post-construction applications. So runoff conveyance is one of the ways that we intentionally control stormwater on construction sites. But how much control do we think about with stormwater from surface stabilization standpoint or a sediment control standpoint? So controlling stormwater is going to require us to understand its impacts. How does it affect the different areas around our project? Are we impacting areas downstream in a negative way? And what are going to be the risks associated with these impacts? And how can we reduce those risks? So on a project, what are we controlling? Well, we have on-site stormwater runoff. This means raindrops falling directly on it. Sheet and shallow concentrated flow leads to concentrated flow, eventually goes to impoundments and our final discharge. Off-site, we have we divert the run-on coming from off-site. We contain it and we isolate it. We try to minimize polluting it further than how it was on site. We don't want to pollute more water that's going to require us to treat it more. And then there's times where we have man-made runoff that we have to deal with. So wash waters coming from vehicle washing, or when we wash tires and things like that, we've got to manage that and control it. We can't let that discharge. Dewatering practices. If we run to a water table that we have to dewater so we can get in there and work. Well, where's that water going? We've got to manage it. And those, also very well controlled. On site, things that we typically don't think about from a control standpoint is going to be the raindrops and the sheet and shallow concentrated flow. It's just something that's there and something that we're impacted by, and we try to manage it, and we try to, throw erosion sediment controls after it, but we really don't think about the control aspect of it, and it's something that I want to discuss today. So again, where's stormwater going? A lot of times when we talk about inspecting sites, good practice is to start at the discharge point and work backwards towards the source, and look at all the things that are happening along the way to determine, what are we doing well, what our deficiencies are. But we shouldn't just think about that point of discharge. What's below our discharge? What are those risks that are going beyond our project? From my standpoint, I'm a relatively introverted person. Meeting new people isn't always fun for me. And, when we think about our neighbors downstream, and what manner do I want to go meet those neighbors? Is it going to be to talk with them and learn about them? They can learn about us, or they're going to come up there because we just polluted their pond or their stream or their property. So, all of that goes back to controlling stormwater, and stormwater really is that catalyst. So as we're thinking about stormwater control, think about kind of three things: tell it where to go, tell it how quickly to get there, and tell it how to get there specifically. So when we're telling it where to go, we've got to think about that distance. How far is it traveling from the point where it starts to, where it's going to next? Whether it's a change in flow patterns, if it's a change in conveyance, or is it going off site? So we've got a distance that we've got to consider for our project. And we got to tell it how quickly to get there. There's a time component to get there. Do we want to get there immediately? Do we want to slow it down so it takes a longer time to get there? And there's things we can do to control that. We can change slope. We know slope affects that time component. We know if we place obstacles in the way, it's going to impede it, or we can put it in detention areas. So we think about the distance it has to go and the time it has to get there. Well, that's velocity. So we manage the velocity from the point where that raindrop lands on our project. We can better manage and control the stormwater within our project. And then tell it how to get there. Think about cross-sectional area, the conveyance method. Is it going in a channel? Are we trying to keep it as sheet flow? Are we trying to put it in a pipe and move it around in a close conduit? What flow state are we putting it in? If we think about this cross-sectional area and we add that to our velocity, well, then that's flow rate. So velocity and flow rate, these are the things that we're all comfortable managing. But if we, break it down into these base components, we can think about better ways to control it. Splash erosion, again, that's the point at where we're talking about water is entering our stormwater is entering our project, and it needs to be controlled. So how do we tell raindrops where to go? Well, what's the destination? Well, it's the ground surface. So how do we direct raindrops on where they can go? We can't stop raindrops from impacting the ground during active grading operations. And we're talking about, in this case, actively grading operations on cut and fill slopes. Or can we stop it? Well, we can put temporary cover, maybe plastic sheeting that provides maximum control. But again, that's a planning and a management opportunity that we need to think about how to control. We can limit areas of disturbance. We don't have to open everything up. We hear that all the time. Minimize areas of disturbance, minimize how much area we've opened up. We think about that as a management, but it's also a control measure. Stabilize, at the end of the day, what can be stabilized. And, Barry Fagan has presented on a project where they had 99% sediment reduction and sediment control by stabilizing what they could at the end of each day. They'd open up only what they needed for that day's work, and then they'd stabilize it before they left. And, if they got caught by rain, sometimes that'd be an issue, but for the most part, they were in control of their site and they're in control of their environment. So it's not always feasible, but again, control is thinking about what we can do, and sometimes what we can do differently in order to get the results that we're looking for. Some things you don't think about: install impervious surfaces as soon as possible. And you may say, well, if we do that, we've got more stormwater to deal with. Well, if you think about how much infiltration you get from a compacted earthen area, it's not much. The increase between a compacted earthen area and a impervious area, as far as volume of runoff, is marginal, I would say, and it's worth gaining that control over having that impervious surface there versus dealing with the managing erosion and sediment on disturbed areas. All right, so how can we reduce raindrop velocity? Again, we're talking about splash erosion, designation, or destination, we're hitting the ground surface. We need to slow the raindrop velocity. It's possible, but the opportunities are limited. Leaving trees in place, that's the best way you can reduce raindrop velocity. Trees will intercept it, detain the drops on their leaves, especially, for summer, spring, fall, when trees still have the leaves intact. They will reduce the amount of raindrops hitting the ground. They will slow that velocity by breaking them apart. Existing ground cover, grass, can do a good job of breaking it up and slowing the velocity down before it impacts the ground surface. And then mulch. Mulch can dissipate energy prior to impacting that soil surface. So we have opportunities to slow raindrop velocity. And then the state that it's in, it's a raindrop. How do we change the state that raindrop is in? Again, it goes back to trees, vegetation, and mulch. Raindrops can be broken apart prior to impacting the soil surface. And by doing that, from a design standpoint, when we're thinking about kinetic energy impacting the soil surface, that kinetic energy can be changed. The kinetic energy of that raindrop can be changed by reducing its mass, by breaking it apart. So Km equals 1/2 mv squared. That's the mass of the raindrop and the velocity of the raindrop. We can reduce velocity, we can reduce the mass, we can control that kinetic energy. All right, what about sheet and rill erosion? Again, these are instances where we got to cover up the ground. We think about erosion control by covering the ground up. But what is that erosion control doing? Controlling stormwater isn't just, what we place on the ground. The soil itself can impact it. The video there on the left shows a sandy loam. Video on the right shows a loam soil. These are the exact same rainfall conditions. And you can see very quickly that through time, the soil itself can impact not only the erosion that it's leaving, but also the state of the stormwater. And as that stormwater starts to concentrate more, then it's going to cause even more erosion issues. So we've got to think about our soils. All right, so again, areas that are being actively graded, cut and fill slips. Where is our sheet flow going? Well, there's options. It could go to sediment barriers, to channels or diversions. It could go to basins. So again, we need to shorten that distance as much as possible. Slope interrupters, decrease the distance between them. Slope drains, again, get the water into a conveyance that's stabilized and move it where it needs to go. Place benching or diversions, again, moving that water around, staying in control of that water for as long as possible. And then temporary detention are going to be options that we have to deal with as well. So covering the surface, again, we've seen the video on the left. We have two options here on the right. We've got just straw mulch placed over it, and then we've got crimped straw placed over it. These are two separate control options. We think about just throwing straw or throwing mulch over it. What is that doing? It's placing obstacles in the way of our project or of our runoff. Crimping it in is going to not only anchor that straw, but is providing another barrier to reduce runoff. And we tested that, and we saw that from a bare soil standpoint, from a 4-inch per hour, 1 hour rainfall event, from that sandy loam soil, we would lose about 700 pounds of soil within that time period. Whereas by just putting loose straw on it, we reduce it by 100 to 137 pounds. Add tackifier to that, increase it even further, reduction of 40 pounds of loss. Our crimp straw actually had an increase of sediment reduction. That's because the crimping itself causes soil disturbance. If we looked at longevity, add more tests to that. Loose straw starts to lose its integrity, but it still does a good job versus nothing at all. Tackifier, we've got to control that and manage that. We've got to keep adding it because that tackifier is going to reduce its overall capability. The crimp straw itself improved, as that first flush and that first storm was removed, the crimp straw itself created those barriers. It slowed and impeded that water all the way down that slope, and it reduced that erosion. All right, so how can we reduce the velocity? Again, same destinations we're talking about for the sheet and reel erosion. Keep slopes shallow, interrupt flow paths. Again, those benches, putting in J-hooks or smile configurations, continuously tracking in the slope, making sure that that slope is tracked the proper way as you're working it, can reduce that velocity, and even on bare slopes can reduce the velocity of the slope and the amount of erosion that we have. Other methods, well, if we reduce the amount of runoff, we're going to reduce velocity. So how do we increase absorption or infiltration into the ground? Mulch and hydromulch can do that. Deep tillage can do that. Topsoil can do that. So these are all means and methods of reducing stormwater runoff. The mulch itself, especially hydromulch, we've tested it. We saw that, for a 2-inch storm over 20 minutes, we had very little runoff from hydromulch because that dry hydromulch absorbed the runoff, became a sponge, and by that means we controlled the stormwater and we controlled the erosion. But we got to get good coverage. We've got to get good planning, and typically, this is going to be something that we only deal with from a finished product standpoint. But again, going back to, can we stabilize as we finish? Well, once we get a section of that area completed, let's go ahead and spray it. Hydromulching is a very efficient means of putting out a ground cover, and it does a good job of bonding to our soil. As it dries, it bonds to the soil, it anchors it in place. And again, there are limits to it. If you get a massive storm come through, it can cause that hydromulch to oversaturate and eventually lose its capabilities. But, we have ways to predict that. We're typically talking about hurricanes and things like that. So ideally, we'll talk about mitigating your risks. There is a little more risk with hydromulch, but for the most part, the rewards are very high for minimizing erosion. Again, slope interrupters, our destination is our channel. Things we can do, again, decreasing that flow path. We have a very steep channel, put these slope interrupters in place, and that's going to reduce runoff velocity. From wattles themselves or slope interrupters, there's not a lot of research out there on best practices. I've got my reservations on whether or not we should be trenching it in or not trenching it in. Hopefully we will be researching this further with a project that we have going on. We're still trying to get some feedback from that, but it's something that we're very interested in learning more about in order to, again, help control stormwater on projects. And then, what state is the conveyance in? How can we impact the state of runoff? We need to keep it, when possible, to sheet flow. That's going to have the least amount of erosive force. Well, again, putting in slope interrupters can reduce that flow path and keep that flow as sheet flow as long as possible. We also want to minimize opportunities for concentration. So that means that keeping slopes uniform, keeping it spread out, free of debris, free of rocks and dirt clods, free of roots, can minimize opportunities for flow to concentrate. Now, what's better than a uniform slope free of debris? Well, how about uniform debris? Grass, mulch, blankets do help keep flow velocities low. Creates kind of a plinko effect where as water's running down the slope, it's running at a much lower velocity. We are affecting, in that case, the conveyance method of it, and hopefully minimizing that erosion. Silt fence can be used, again, but it's something that you need to plan for. You probably don't want to run silt fence all the way across. Think about ways to plinko it down the slope, stop it, delay it, and let it go down to the next device. Keep it covered, and then things like brush barriers could be opportunities for that. we have opportunities for using sediment barriers once it gets to the bottom. Sediment barrier is a temporary structure that's used across the landscape. It intercepts sheet flow to reduce velocity, erosive energy, and impound runoff. Again, we're trying to promote sedimentation, but we are affecting the stormwater from that standpoint. There's a lot of sediment barrier options out there that we can utilize. We did some testing at AU.dot for this. One is the silt fence installation method that they use. And again, we're trying to impound runoff. If we're going to control that stormwater runoff, we got to keep that impoundment. And so that means a structurally sound device. What we found with the old installation method of light T-posts and 10-foot spacing, we weren't controlling runoff if we got enough storms, and we would get failure. So again, this is not controlling stormwater any longer. This is hopefully mitigating and minimizing the impacts of that loss. So went through, did a lot of testing on how to improve it, decreasing post spacing, going with heavier T-post, offsetting the trench, were all means that we found to better influence the impoundment capabilities of our silt fence. And by doing that, we reduced the opportunity for overall failure. So by reducing failure, again, we are controlling the stormwater. We're maximizing sedimentation. And something that we found throughout this testing is, our impact of controlling the impoundment allowed us to control water quality. We are capturing sediment upstream. We're capturing 95% of the sediment upstream of this, but we also want to see our impacts on water quality throughout our treatment train process. And so through testing, we would go in and we would, evaluate, the water that we're introducing. We evaluate the water quality on the water surface. We evaluate the water quality at the bottom of the surface as that water is impounding to try to better learn, how silt fence is impacting the water quality from a sediment control standpoint. But we also want to look at what happens coming through the silt fence and then the final discharge. When we look at the turbidity as a result of this, the interesting thing that as depth increased with our silt fence, the turbidity at the bottom of our water column was the greatest, and it stayed that way throughout the entire storm event. And I'm not showing the sampling location 4, which is the downstream point where we sampled right through the filter fabric itself, because it almost exactly mimicked the SL3, the stormwater location 3. So, that worst case scenario, that stormwater at the bottom of the fabric was still coming through the fabric itself. The cleanest water we found was at the water surface at the top. And so managing that stormwater increasing impoundment depth, as we see as depth increased, the water quality in the top of the water column, that green line, improved over time. And then once the storm stopped, even the water quality upstream of that sediment barrier drastically improved. As soon as that 30-minute mark hit and we went to that dewatering phase, the water quality, the turbidity dropped substantially. So again, upstream versus downstream, when we're taking water quality samples through the fabric does not filter. When we saw that over and over. So thinking of these as a filtering device doesn't put us in that means of controlling the stormwater and controlling erosion and sediment. So clogging is a good thing. The non-woven filter fabric that we use for AU.dot Type A State of Alabama stormwater sediment barriers clogs very quickly. And as long as we are anchoring it and bracing it well enough, it's going to provide that means of controlling stormwater and means of controlling sediment on our project. Now, one of the things that we found is by the time we use this easily clogging fabric on this device that doesn't structurally fail any longer, that stormwater would just sit there. So unless it's going into the ground, it's not really moving. So we thought we need to come up with a way to dewater it, but this provides us an opportunity to further control it. So the worst thing that can happen on a lot of projects is when water overtops a silt fence. And that's going to happen at that lowest point. So if we can put in a overflow component of our sediment barrier, like this dewatering device where we have a weir in it, we can direct where water is going to discharge to. We can ensure that where it's overflowing, It's not going to cause erosion and failure modes from the downstream scour, but we're also getting the impoundment capabilities that we're looking for. So a lot of options for us to deal with is, again, it's about controlling the stormwater. Other options besides that, type A fabric is going to be the type E option. We've got woven fabric, silk fence, and wooden posts. But the thing to think about is, how long are you control of this? Those wood posts probably last in our climate about a year. And that's tops. They start breaking after that. So you got to think about how long you need this device to be in place before it fails. Again, what are other control approaches that we have? Well, when water's running perpendicular to, or when the silt fence is perpendicular to flow, smile configurations are going to be key. When it's parallel to flow, things like J-hooks and tiebacks are going to be beneficial. So, these are common areas that you see on a project. We have a slope where water's going to run down it. It's going to hit the fence, but there's also a lateral slope to it where water isn't just going to stop against that fence. It's going to continue downstream to the bottom of the hill where the channel is. By putting in J-hooks, you are managing the amount of runoff that's going down there. You're controlling it, reducing flow path. And if you look at the other side where we didn't put in these J-hooks, how much control do we have of that stormwater when it gets to the bottom? The velocity is going to be higher. We have less impoundments that we can manage, and there's much greater chance of failure. Spout configurations, biggest things we need to consider is it going to discharge over top it, or is it going to discharge around it? And putting them in kind of a configuration so that they work their way downstream. Is this silt fence controlling stormwater properly? Well, we see that's not tied back up the slope adequately enough, and we see the sediment downstream of it. So obviously this is a case where it's not. We see, is this an instance of stormwater being controlled properly? Well, this is a lack of control within the silt fence. We have structural failure. And again, thinking about where stormwater goes, this is right at a inlet grate. That means that this area was designed for stormwater to go to this point. So this is a point that we need to make sure that we reinforce and minimize our opportunities for failure. Common sense approaches, we don't have to use silt fence all the time. Alabama Power came to us and said, we've got a lot of slash mulch from these utility projects that we have. We don't want to waste this natural resource, and it's also good business not to have to haul it off. So can we use this from a sediment barrier standpoint? And, looking at the pictures that they have, it looks like, by intercepting flow, they're able to capture sediment very easily. So we took these mulch berms and we put them in our project test area, and we found that the flow passes through the mulch, but it does it very slowly. There's minimal impoundment, and it discharges faster than silt fence. And so those may say to you, well, we're probably not controlling stormwater enough. But spoiler alert, this actually filters. So we set that in our test area. We put it in a way where we didn't capture any additional sediment from the installation. We didn't need it. There's no, sod staples or silt or T-post or anything like that we had to manage. And we abutted it to the downstream side so that when it discharges directly into our downstream containment system. And what we found by doing this is, yes, we get sediment capture upstream, but look at the impoundment. You can see the mud is barely built up, maybe less than a foot on the upstream side. So, we're obviously not detaining it for a long period of time. During this testing, we put in over 1.5 tons of sediment. And what we found is we'd get about 88% retention upstream. So pretty good. Not as much as silt fence, but very good. When we looked at what we were capturing downstream, meaning that in our containment box, we went and we dug out only 57.5 pounds of sediment out of the 2.5 tons that we put in. So everything else between the upstream side and the downstream side was captured within that slash mulch berm itself. So we had a 98.2% sediment capture through this installation. When we get to, gully erosion, unfortunately, we're at a point where we've lost control. We don't know where it's going. We don't know how to control the velocity, and it's out of control from a conveyance standpoint. So this is kind of the worst case scenario for us. So gully erosion means there's a lack of control. When we do want to concentrate channelized flow, we're thinking about it's going to go to inlet structures and detention basins, discharge outlets, open areas. We need to control how it gets there. But we're in a design and constructed conveyance, so we do have a much greater measure of control. How do we reduce its velocity? If we think about Manning's equation, that means that we want to increase roughness. Over here, we've got different roughness factors. That N on the bottom from a velocity standpoint means the larger the N is, the lower velocity is going to be. We decrease the slope. As we decrease slope, if we get slope to zero, velocity goes to zero. And then we can put obstacles in the way, check dams and things of that nature to reduce velocity. Again, from a destination standpoint, we want to interrupt that flow, minimize opportunities for constant concentration throughout our project. So when we put ditch checks in as our means from an obstacle standpoint, a ditch check is a small barrier that's going to reduce channel erosion by flattening the gradient of our flow. So if we look at flow and we think about minimizing channel erosion, if we think about allowable shear stress within an earthen channel, the allowable shear stress is only 0.03 to 0.1 pounds per square foot. 4 inches of water and a 3% slope, doubles, triples that amount of shear stress. So very quickly, we lose our ability to manage the amount of sediment that we're creating, amount of erosion that we're creating. We can put things like TRMs in place, and we can vegetate it. And as long as we are in that low depth flow, then everything can be good. Everything can be stabilized for minimizing erosion. But, as our flows increase, as our depth increases, even putting in erosion control blankets and things of that nature can greatly be diminished by high velocity flows and channels that are pretty deep. So putting in control measures like check dams, ditch checks, can reduce and flatten that energy grade line or that hydraulic grade line, which is that even though our slope is somewhat steep, the slope of the hydraulic grade line or that water surface approaches zero. And as that approaches zero, then our shear stress approaches zero. So we are reducing that shear stress and erosive impacts. But that also means that we've got to design it correctly. We've got to have check dams that are in place that are spaced properly. And we also have to have check dams that are in place that impound properly. So there are going to be areas where if it's not impounding correctly or it's not reaching the upstream check dam, then we're going to have high velocity eroded channels. Things that we can put in place for this is going to be riprap check dams with chokers. Just riprap itself has high velocity going to it, a lot of flow rate. It doesn't impound very well. We can add choker stones. We can add filter fabric on the upstream side, and that can greatly increase our impoundment capabilities, further controlling the stormwater. Wattles, same thing. We want to be able to control it. Again, they don't do a good job of filtering. This picture says 1,000 words. The sediment laden water comes in. We can see it's actually flowing through this wattle particularly, and on the downstream side, the water clarity looks exactly the same. But what do we need to do to control stormwater? We can't let it go under it. So we've got to put in some type of underlay to keep water from eroding up under the check dam. We want the wattle to have good contact, again, to minimize the water from going under it. We want to go through it and over it. And so that A-frame TP staking is going to be better than just downstream staking. But the best thing you can do for wattles is going to be these little sod staples. Putting them on the upstream and downstream side is going to decrease the water going under it and force it to go through it or over it, again, managing the stormwater itself. We can use silt fence as a check dam, but we need to be careful in how we're doing it. And putting in a weir within it means that we are keeping the water contained within the center of the channel where it's expected to be. And it's going to allow us to stay in control, minimize erosion, maximize sediment capture. When we tested this, this type of mean and method could capture 91% of the sediment introduced. We can do things like add sumps upstream to further treat stormwater, to capture and contain some of it post-storm and let it fall out of suspension, but also provide more capture volume for the sediment upstream. And this is an interesting evaluation of how the performance of this practices perform. We can see this is, again, a mulch check dam. It doesn't impound as much. And where's the sediment? It's much closer to the device. Whereas with a silt fence ditch check, that sediment stays much further back because that impoundment is much further back. So again, controlling the stormwater controls the erosion and the sediment within our channels. Again, looking at these pictures, this is the stormwater control. Again, we didn't take into consideration what needs to be done. We just kind of went through and did what was expected. This poor guy always makes me laugh. He's not in control. He's sad and lonely. And again, something that we're not really in control. So I want to take a little more time and talk about inlet protection practices. I'm not going to get all the way through where I wanted to from the sediment basin standpoint, but we know sediment basins do a good job of controlling stormwater. Inlet protection also controls stormwater. There's a lot of different ones out there, but again, if we're not putting them in properly, not planning correctly, we're going to cause issues. We've got to control where stormwater is going and how it's getting there, and things like flow bypass, things like flooding, elevating safety risk are concerns that we've got to think about and think about better ways to control that stormwater. Undercutting, just like with the ditch checks, we've already talked about it. That's going to cause problems. We're not managing the stormwater, controlling how it's going and how it's getting there. And then obviously maintenance is going to affect it. Now, again, from a control standpoint, this is just a really neat example that we found that, sometimes the best intentions result in poor performance because we don't think about we think about, putting in practices that are going to control sediment, but we miss the point of controlling the stormwater. We've all seen these devices, these domes you put over inlet protection, and yes, it's going to reduce the amount of sediment going into that inlet. It can also stop the water going into the inlet. These inlets are there because the stormwater was intended to go there. It's designed to dewater a certain drainage basin, and if we are deflecting that water downstream, well, what happens? Well, we're going to end up causing flow bypass. We're going to cause overwhelming. We're going to potentially cause a point of failure. And that point of failure, through that overwhelming component, led to a loss of control from a stormwater standpoint, but also erosion standpoint, and also a sediment standpoint. It affected downstream BMPs, caused failures, and eventually we ended up with a sediment yield that we likely did not want to see from our project standpoint. So I'm going to pause right there. I do want to pose a question. I'm going to back up real quick because I do want to pose a question for you guys. And it's just something I've been thinking about, something I want to consider from a stormwater control standpoint. It's something that I've never really thought about before. I just talked about this earlier, how we want to control stormwater by managing, flow through, getting that hydraulic gradient slope as close to zero as possible, reduce these areas of highly eroded channels. And if we cause our check dams to overtop, then we're going to maximize that entire impoundment capability. And something I've been thinking about is, do we need to have a minimum check dam or ditch check impoundment length? We know that the impoundment length is a function of both the slope of the channel and the height of the channel. But if you start getting these slopes, so we have, channels at 10%, well, for an 18-inch check dam, our impoundment pool is at best going to be 15 feet. And over 300 feet, that's a lot of check dams for one. And for two, at 10% slope, 15 feet is not a lot of time for that impoundment flow to reduce velocity. So maybe for channels that are steeper, we start thinking about increasing impoundment or flow depth within the channel and check dam height if possible, so that that height of the check dam is going to push that flow again further back upstream, increasing that impoundment length and increasing that spacing, and hopefully that'll allow us more opportunity to slow that water down, capture more sediment, and reduce the amount of sediment that's leaving our project. So I want to leave a few minutes for questions if possible. We got about 10 minutes left, so we can open it up to questions.
So, all right, thank you, Wes. Everybody, at the bottom of your screen, you should see a Q&A tab that you can click on, and then any questions you may have, enter them there, and Wes will go through and answer them. I just wanted to remind everybody that there will be PDHs associated with this, so just keep your eyes on your inbox, and you should be getting an email soon. And then, Wes, if you don't mind, you could share your email in the chat in case we do have some participants who don't have a question quite yet, but maybe have it on the back end so that they can reach out to you regarding your presentation.
Yeah, anytime you guys have a question, concern, comment, feel free to reach out to me. Again, I've been with the stormwater facility for a long time. We've got a lot of different components out there that can, I hope, help out issues that may arise on your projects. I get we have stormwater classes or field days and installer training, and I get people call me all the time or send me emails that I was attending those courses and say, hey, I saw this or I saw that, and I'm looking for ways that we can implement this or better manage it. So feel free to email me at any point, and I'm happy to help where I need to. So one of the questions that we have is, have you ever tested any options other than wire mesh backing for silt fence? And the answer is yes, we have. We tested what we'll call the big box store silt fence. And what we found is that it tears very easily, falls apart very easily, doesn't last very long. Now, obviously, that's not something that we want to see on big construction sites, but we were curious, and it lasted about 2 minutes in our test area. We did a project, or we were working on a project with Nebraska DOT, and one of their silt fence, or actually their silt fence in general, doesn't have wire backing. Their concern was wire backing is going to be another pollutant or another source of waste that they didn't want to have on their project. So we tested it in a 10-foot wide channel as a check dam essentially, and same thing. It tore pretty quickly. We tested it in our sediment barrier testing area. It tore some under sheet flow conditions. A better fabric can hold on, but the amount of sagging that occurs with it takes that 24-inch, 30-inch silt fence that you installed and renders it down to maybe 12 inches. It just kind of falls over. So the wire backing, the mesh there is there, and it's important. During SWIP development, is there a method to estimate the volume of mulch that will be generated from site clearing activities to help determine whether sufficient material will be available for berm installation? That's a great question. And that's honestly a question AU.dot has kind of posed to us, something we've been talking about. And honestly, that's probably a better question that we need to be asking other professionals. I know forestry professionals can go in and look at sites, come up with stumpage requirements, and from there get an idea of probably how much mulch that you can produce from the trees that you're planning to clear. So from that standpoint, I think it's something we probably should look into and get a better idea. Because you're right. If we want to use that on our site, if we're planning for it, we need to know what's going to be available. And if we don't have enough available, we need to be able to take and add to it and supplement it with more traditional BMP. So that's a great question, something that we're looking to answer. I know this is primarily dealing with control during construction phase, but for post-construction phase, what have you found to be the best stabilizing method for slopes, vegetation, for slopes? I guess is that vegetation or riprap? It's all about, the type of vegetation that you're using. If you're going to use vegetation, you want it to be not just turf grass. If you have a lot of flow going over it, depending upon the steepness of the slope, you want to look at vegetation that's rooted deeply. If we can get vegetation with deep roots, and part of that is going to be soil prep. It's going to be going in and doing that deep tillage, loosening that soil up, putting into good topsoil. That's going to allow those roots to get as deeply as possible, and vegetation will work. Riprap obviously will work. It comes with a different management requirement, different cost component. We see it all the time, especially up north where they have a hard time with slope failures and things of that nature. They just line the entire slope with riprap and it does a good job. It's not aesthetic. And all those things go into the BMPs for post-construction. But something that should be considered. If you have a steep slope, what BMPs would you recommend instead or in addition to check damps? For steep slope channel, I think you're getting into a combination of things, and it may be riprap, it may be going into an articulating block like field track or Fleximat, but something that's going to have a higher shear stress relief, but also adding in check dams to again slow that velocity down. If we can armor the slopes, armor the channels, and slow the velocity down, combining BMPs is going to be the best way to mitigate those problems. There's a question in the chat. Is there a BMP specification for the mulch berm for sediment barrier available? Yes. Short answer, yes. We created one for Alabama Power. It may be on our website. Again, my email's there. If you want to email me, I can make sure that we can get that in your hands so it can be utilized. And Matt, it's probably something, if it's not up on our website, we probably should get it added so that it is available for folks to use within our state. Nebraska allows it as well. And so they have their own specifications, a little bit different, but those are available for different states.
All right. Well, thank you all for your great questions. Again, thank you, Wes, for volunteering to be a presenter with us today. As I've mentioned, everyone should be getting the PDH email soon, and we will see you all again next month. Thank you.
Thank you, everyone.